All right, today we'll talk all about the determinant and a little bit about trace. So these are very important scalars that capture property of matrices, just like the average and standard deviation capture some important properties of a set of data, like a set of exam scores. So trace is very simple, so we'll talk about that first, and then we'll spend the rest of the time talking about the determinant. So it's very simple to compute. We won't get into all of its interesting properties, but there is an application to Heisenberg uncertainty principle that matrices can't model this physical effect. So let A be an n by n matrix with coefficients aij. Define the trace to be the sum of the diagonals. So for example, if A is this matrix, then the trace is 5 plus 1 plus 6. And that's it. It's very easy to compute. Here's some properties that you can explore. So if I have two matrices that I can add or multiply, then the trace of A plus B is trace A plus trace B. Also, trace AB is trace BA. But something subtle is if you have an arbitrary product, it actually doesn't commute in all different ways. It's just in this way. You can move the leftmost matrix to the right side. Um, we talked about eigenvalues a little bit last time, and the trace of A is equal to the sum of the eigenvalues of A counted with multiplicity. So the first property is easy to prove, and the second one requires some work. We've seen 3 in the case of a diagonal matrix, since diagonals are equal to eigenvalues in a diagonal matrix. And counted with multiplicity means that if the eigenvalues are 2, 3, and 3, like if you had a diagonal matrix with 2, 3, and 3, then the sum is 2 plus 3 plus 3, not just 2 plus 3. So we haven't found out how to find the eigenvalues 2, 3, 3 versus just 2 and 3 with the methods we've learned, but there are methods to find them. And you usually get a polynomial. So for example, the polynomial x minus 2 times x minus 3 squared, then the eigenvalues are the zeros of this polynomial. So it has zeros at 2 and 3, but 3 has multiplicity 2. It appears as a root twice in some sense. So here's an example. We can prove that there's no n by n matrices A and B satisfying AB minus BA is the identity matrix by using trace. So the trace of the identity matrix is just n, because it's 1 plus 1 plus 1 n times. But the trace of AB minus BA, we could split up sums and also differences. And then trace BA is trace AB. So these are equal and you get 0. So for any matrices at all, trace AB minus BA is 0. So it can't ever be equal to identity matrix. Okay, let's talk a little bit about determinants for smaller size matrices. So this is much more complicated. There's many ways to define it, and we'll see 2 of them. We won't prove they're equivalent, but they are. First, we'll talk about the usual method in linear algebra, the recursive definition. And then we'll talk about a more algebraic abstract definition involving permutations. So a determinant for a 1 by 1 matrix is just the number inside. For a 2 by 2, we've actually seen it before, because if ABCD is invertible, we had a formula for A inverse. It was 1 divided by AD minus BC times D minus B minus CA. And the denominator AD minus BC is actually the determinant of A for a 2 by 2. Now we could define the determinant of a 2 by 2 and then a 3 by 3. And these definitions are misleading because we'll have a pattern, but the pattern doesn't continue. And we'll see that the pattern doesn't continue at the end of this lecture using a different definition. So let's say I have this 2 by 2 matrix, then the determinant is just AD minus BC. And the notation for determinant uses these vertical line brackets. So the determinant of ABCD is the determinant of ABCD, which is AD minus BC. And we could visualize this using the following diagram. So you have left to right diagonals, AD, and right to left diagonal, BC. So you add up AD and you subtract BC. So for 2 by 2s, it's very easy to compute. And we could check for a 2 by 2 that the determinant is 0 if and only if CD and AB are multiples of each other. So if AB is like 3CD, or if CD is 0AB, then the determinant is 0. That's if and only if, actually. And for a system of equations, we could check that there would not be a unique solution if one row was a multiple of the other, because then we would have two equations that were either inconsistent or multiples of each other. So in the first case, we would get no solutions. And if they're multiples of each other, we would get infinitely many solutions. What about a 3 by 3? We didn't learn the inverse of a 3 by 3 because it's much more complicated. We'll see later. So we haven't applied this yet. Let A be the 3 by 3 matrix, this one. Then the determinant is AEI plus BFG plus CDH, all of the left to right diagonals, including wrapping around the matrix. So you see we kind of, let me get a marker. We kind of wrapped around back to G. And C wrapped around to D and H. Oh, sorry about that marker. I don't know what happened. And then the right to left diagonals are negative. So CEG, and then BD wraps around to I. So that's why we could draw it as BDI over here. And then A wraps around to FH, which is why we could draw it right here. So this is called the rule of Saris. We multiply along these arrows. We add the green products and subtract the red products, just like you did for 2 by 2s, more or less. But the wrapping around was different, right? If we wrapped around BC, that could have been a left to right diagonal. But for a 2 by 2, we don't wrap around, and this is how we do it. For a 3 by 3, we wrap around. We could also write it recursively in terms of 2 by 2 determinants called cofactor expansion, which we'll study a little bit more soon. You could check that this product that we wrote is equal to this. You do A times this bottom 2 by 2 matrix. So you look at A and you delete the row and column that it's in, and there's a 2 by 2 matrix left over, and you take the determinant. And then you take B and you switch signs, make it negative, and you have DFGI. And then C, you have the 2 by 2 DEGH. And you could check by computing this. You really get AEI, BFG, CDH, minus AFH, minus BDI, minus CEG, which is what we had up here in this formula. So here's an example. Let's go back to this matrix that we used to compute the trace, or that we computed the trace of. So we can compute its determinant in a few of the ways we've learned. So we can first try the method from figure 1, this figure here, the rule of Saris. So you look at 516, 874, and 293. And then you subtract 573, 896, and 214. So we added and subtracted all those possible diagonals. So you get 237 if you do this method, or minus 237. The other way was cofactor expansion, which the formula said is this formula. And notice that the 516 appears just like it did up here, and minus 573 appears just like it did here. And then minus 896 appears, minus minus plus 7874 appears, and plus 293 minus 214 appears. And so we don't have to compute it. It's just equal to what we already did up here. So it's minus 237 as well. So let's talk more about what it means to compute via cofactors. So let's talk about what it means to be a minor and minor determinant. So let A be an n by n matrix. Define the ij minor of A to be the n minus 1 by n minus 1 matrix that removes the ith row and jth column, just like we did above when computing the determinant of the 3 by 3. And then define the minor determinant, Mij, when we have just one matrix in mind, right? Otherwise, it depends on A. That's the determinant to be a determinant of the ij minor. So you take a look at A, the 1, 1 minor removes the first row and the first column. So you have this left over. It's a 3 by 3 matrix, which is 4 minus 1 by 4 minus 1. 503, 010, 041. And then we could take the determinant and we compute that it's 5. So M11 is 5. The 2, 3 minor is remove the second column and, second row and third column. That's 10 minus 6 minus 100, 201. Then M23 is 0 because you have a 0 column. And whenever you have a 0 column, the determinant will end up being 0 because algebraically you could think about it. Use the rule of Saras. Every single product has a 0 in it, so it's 0. Or you could think about it as a system of equations. It's a system of equations with three unknowns and 3 equations, but y doesn't appear anywhere in the equations. That means y could be anything if those equations are true. So there's no unique solution. And the determinant is 0 if and only if there is not a unique solution to the system. We didn't prove that, and we're not going to prove it, but that's a fact. If the determinant is 0, actually the determinant is 0 if and only if your system does not have a unique solution. So let's talk about determinant using cofactors. So you have your n by n matrix and call Mij a minor determinant of A. Define the ij cofactor to be Mij times a sign that depends on where you are in the matrix. Minus 1 I plus j. What this looks like actually is it makes a checkerboard or a chessboard on your matrix. That's 1, 1. This is 1, 2. This is 1, 3. This is 2, 1, 2, 2, 2, 3. So there's a checkerboard on your matrix with pluses and minuses. And if we look at this minor, then there's a plus sign with it. And if we look at some other minors, the signs depend on which ones you took. For example, when we took B times the rest of it, B from the above example, it was minus B times the 2 by 2 matrix. So let's go back and take a look at that. We had minus B because 8 appeared in the 1, 2 entry, and 1 plus 2 is 3, which is odd. So in all of the I plus j odd places, you get a minus sign for the cofactor definition. So you could define the determinant using cofactors. This is a typo. J isn't appeared yet, sorry. So the determinant is this if you just remove the first column. But here's a result. If A is an n by n matrix, then actually you can remove any column and take cofactors, or remove any row and take cofactors. So this is a definition, but it's actually equivalent to taking any column or any row at all. So that's really interesting. You could also prove using this definition that determinant of A is the determinant of A transpose. So for a 2 by 2, it's still AD minus CB. So for 2 by 2, that's easy. And now you can use induction if you know how to use induction. So let's use cofactors to compute this determinant. Here, I goes from 1 to 2. So you get A11C11 plus A21C21. A11 is A, and it's in the 1, 1 spot. So you get a minus 1 to the 1 plus 1. C11 is the matrix left after we remove all of the rows and columns containing A, which is just the 1 by 1 matrix D. That's the cofactor in this case, times the minus 1 to the 1 plus 1. And then we look at the second entry. Oh, I should have done C here, actually. So this is a typo. I should have taken the first column, so should be C times minus 1 to the 1 plus 2 B. But anyway, it's the same. It's still AD minus BC. And there are three other ways to take the sum of cofactors. You could remove the second column, or the first row, or the second row, and each of them will produce AD minus BC. So for example, A2J, this removes the second row. So it's A21, C21 plus A22, C22. A21 is C, then the cofactor is minus 1 to the 3B. So you get minus CB. Plus D is the A22 entry. C22 is minus 1 to the 2 plus 2A. So it's minus CB plus DA, which is AD minus BC. Okay, let's go to the 3 by 3 matrix. And we define the determinant to be exactly this thing for using cofactors above. So we define the 3 by 3 cofactor expansion before the general one, and we define it this way. So you see we get a plus A, AFHI, minus B, DFGI, plus C, DEGH. And for the first cofactor, we remove the first row and the first column containing A. The second cofactor, we remove the row and column containing B. And for the third cofactor, we remove the row and column containing C. And in practice, you want to use that theorem that we can remove any row or any column to remove the simplest row or column that make your computations easiest. So for example, if we go back to this 4 by 4, where we had examples of a cofactor, the easiest one is usually the one that contains the most zeros. So let's remove this column. So what that means is we're going to sum over the second column. That's what I mean by remove. We're going to sum over the second column. So we have 0 times something, and then we have plus 5 times something. That's the A22C22 part. A12 is 0, A32 is 0, and A42 is 0, so those go away. That's why they don't appear in the sum. And all we're left with is A22C22. So this determinant of this 4 by 4 matrix is basically just the determinant of a 3 by 3 matrix. And if you do all this computation, you get 205. And here I even expanded the cofactors for the 3 by 3 just for fun, using the second row, which you could take a look at. So we did minus 1 times minus 1 to the 2 plus 1, 4 minus 6, 4, 1. And we had a 0 here, and so one of the cofactors didn't appear. So this 3 by 3 reduced to just a 2 by 2, but rule of Saros is usually the simplest thing to use to compute determinants for 3 by 3, the simplest formula. And here we computed a 4 by 4 determinant. But this is very long to do. Like if we didn't have these zeros, imagine how long it would take. We would have 4 3 by 3 determinants. So in general, if you have an n by n determinant, it requires n many n minus 1 by n minus 1 determinants. And each of those require n minus 1, n minus 2 times n minus 2 determinants. So this grows like n factorial, the number of computations you need to take. So because of this, you want to take cofactors along a row or column with the most zeros or simplest looking numbers like plus or minus 1 if you don't have any zeros. Let's talk about Cramer's rule and other applications of determinants. For now, it's pretty mysterious what these are and why we're just defining them. But here's something interesting. So geometrically, if you have a parallelogram in the plane, so a parallelogram, once two sides are defined, the other two sides are also defined. And so let's say this one is AB, and this vertex is CD. Then the area of the parallelogram, surprisingly, is AD minus BC. It's the determinant of the matrix ABCD. So geometrically, this has applications, and in three dimensions too. If I have a three-dimensional parallelogram called a parallelepiped, so this is hard to draw for me, but it's a four-dimensional thing, or sorry, it's a three-dimensional thing now that looks like a parallelogram, but in three dimensions. And if it's generated by three of these sides, the others will be completely determined. And the sides are have vertices at A, B, C, D, E, F, and G, H, I. Then the volume of this thing is actually the determinant of A, B, C, D, E, F, G, H, I. And you can use algebra to prove this. So you could set up systems of equations, with cosines, sines, whatever the angles are, and you'll see that they'll end up depending on ax plus by and cx plus dy. And the determinant, ABCD, will appear somewhere in your computation. So Cramer's rule is one reason why the determinant appears. Assume you have ax equals b. That's a system of linear equations where a is invertible and b is a column vector. Then we could solve for x by using determinants the following way. So let AI denote the matrix A with the ith column replaced by B. So A has a bunch of columns, and we're going to take the ith one, and instead we're going to insert B in here. But all of the other columns stay the same. So that's AI. So if the entries of X are denoted by XI, we could actually solve for X. XI is equal to determinant of AI over determinant of A. So using determinants, you could solve for the variables in your system of equations. So Cramer's rule tells us that to find X, which is A inverse B, we just need to find determinant A and determinant of A1 through AN. So we need n plus 1 many n by n determinants, which is a lot. It's basically like 1 n plus 1 by n plus 1 determinant. So here's an example. We considered the following system of equations in chapter 3, which we solved using row echelon form or reduced row echelon form. So if we set up our matrix, we compute it using rule of Saris. The determinant is minus 22. B is 11 minus 12 minus 5 in this case. Cramer's rule tells us X is determinant of A1 divided by determinant of A. Here's the determinant A. And here's determinant of A1. So we replaced the first column, 4 minus 3 minus 2, with B. And we left everything else the same. If you compute this, you get minus 44. So you get 2. And this is a footnote that I'll mention later. For y, it's 1 over minus 22. We replace the second column with b and compute the determinant. We also get 2. And determinant of A3 is going to be, you replace the third column with b and take the determinant, you get minus 1. And the computations are here if you are curious how to add those numbers. And this matches the solution we got in chapter 3 using row echelon form. The solution was 2, 2 minus 1 for x, y, z. And for 2 by 2 matrices, this is really simple. So let's just solve in general a 2 by 2 system. You could plug in any numbers you have anytime now. Use this formula. If I have this system where I know A, B, C, D, E, and F, and I don't know X, Y, then X and Y have unique solutions if and only if the determinant of A, B, C, D is not zero. And in that case, Cramer's rule tells us X is AD minus BF over AD minus BC, and Y is AF minus EC over AD minus BC. And Cramer's rule is related to the following fact. If A is an invertible n by n matrix, then A inverse exists if and only if determinant isn't zero. And in this case, we could solve for the entries of A inverse using cofactors. The inverse of A, ij entry, is the Cji cofactor over determinant A. So if we know the cofactors and we know the determinant of A, we actually know A inverse. And we could prove this. Let's multiply A together with the matrix B defined with these entries. And everything will follow from the definition of determinant because it's defined using cofactors. So everything's going to end up canceling out. So together with the unproven fact that determinant is independent of what cofactors you take, which hopefully you learn someday, but we won't be talking about it in this class. So A times B is this by definition. This is how you multiply matrices. Then this is equal to this sum. And the BKJs are just defined by this. So I replace JI with K. And I plug this in. Here's what you get. Now, if I equals J, then this sum is exactly determinant of A by the theorem. AIK, CIK, that's exactly what we had up here somewhere. AIJ, CIJ, that's the determinant of A for any J, including, or for any I, for any I in this case, since K is already the variable we're summing over. So this is determinant A, just the formula for that. So ABII, the II entry of AB is equal to 1. So now recall that the JK cofactor is this thing. So it looks like we've removed the jth row. Like we're summing over K. So we've removed the jth row, and now we're summing over all the K columns that get removed by removing the jth row. In general, this sum is the same as the determinant of this thing. So if we insert the jth row, except in this case, the jth row is AIK. Right? If I was J like above, up here, then this would just be the determinant of A. But this is not A, this is a different matrix with row AIK in the jth row. But when I is not J, this matrix has jth row equal to the ith row because the ith row also has entries AI1, AI2, and so on. But the matrix equation AX is B won't have a unique solution, again, because two equations are repeated. And I claim that the determinant is 0 whenever this happens. So this determinant is actually 0. So what we showed is the II entries are 1, and the ij entries are 0 whenever I is not j. And that's the proof. So we proved AB is identity. You could also do it the other way because inverse needs to be two-sided. So you also need to check BA. But one of these will use the fact that you could sum over any row and take the cofactors of any row, and the other one uses that you can use cofactors over any column. So the proof is pretty much the same. Now we could prove Cramer's rule as a corollary to this formula for determinants. So let AX equals B. So X is A inverse B. By the matrix product formula, the entries of X must be equal to this. I write out what Xi is in terms of sum. So I'm multiplying determinant on both sides just to make the writing a little easier, not having a fraction later. Then Aij inverse is Cji divided by determinant. But this is just the formula for determinant of AI, because you could think of it as the sum of an expansion of cofactors of AI just by replacing the ith row with bj, or with b, I mean. So that's it. I mean, it's very similar to this idea up here, but with the ith column of C, or with the ith column of A. So here's some theory and properties of determinant. Let A and B be matrices that we can multiply and add. Then determinant of AB is determinant A times determinant B. In particular, determinant AB is determinant BA, just like trace. But for determinants, you can reorganize them any way you want, because you can reorganize real numbers any way you want because of commutativity of multiplication. The determinant of identity matrix is always 1. And from the above two properties, if A is invertible, you could show determinant of A inverse is the determinant of A inverse. And in general, in mathematics, if you can commute words like determinant of inverse is inverse of determinant, then something magical is happening. So in this case, this is really magical. Even this, determinant of product is product of determinants. You can invert it. Or determinant of identity is identity. The determinant is the product of eigenvalues of A, counted with multiplicity. Now, the last three properties have to do with elementary row operations. If B is obtained by the elementary row operation, multiplying a row of A by C, then determinant of B is C times determinant A. So if one of the rows or columns of B is multiplied by C, it changes the determinant by C. If B is obtained by adding a multiple of a row of A to another row of A, then determinant of B is determinant of A. Adding multiples of rows doesn't change the determinant. And if B is obtained by the elementary row operation swapping the ith and jth row, then determinant of B is minus determinant A. So swapping rows or columns because of the A transpose property of determinant changes the sign of the determinant. And there's a lot more properties of determinant as well. So now let's talk about the definition of determinant using permutations. So a bijection, a one-to-one and onto function, so it's a permutation. It permutes 1 through n. This is called a permutation. So the 1 could be anything, and then 2 has to be one of the remaining n minus 1 things, all the way down to when there's a unique choice left for n. The set of permutations is denoted by Sn, and the sign of a permutation can be defined with this complicated looking product. And since sigma is a bijection, this simplifies to plus or minus 1, because j minus I in this term will cancel out with a j minus I or an I minus j in some other term. Since we're taking the product over all possible ij, it'll eventually appear, which is not obvious. But yeah, the sign will be plus or minus one. If the sign is one, we call the permutation even. And if the sign is negative one, we call it odd. And you should check that there's n factorial elements in Sn. So n factorial total permutations of n elements, just like shuffling a deck of cards. So there's 52 factorial possible ways to shuffle a deck of cards. If sigma and tau are two permutations, then the sign of the composition is the product of the signs, which is interesting too. And this justifies the names even and odd, just like adding numbers. If I take a product of two even permutations, I get even. If I do odd and odd, I also get even. And if I do odd and even, I get odd. So permutations have a few different notations. I'll introduce one and then start using another one later. So here's one where we write the domain and we write the range like this in order. The inputs are on top and the outputs are on the bottom. So here, sigma 1 is 2, sigma 2 is 1, and sigma 3 is 3. If you draw lines between the inputs and outputs, making sure no three lines intersect in the same place like this. So 1 went to 2, 2 went to 1, and 3 went to 3. And now we're going to match 1 with itself, match 2 with itself, and match 3 with itself. Then there's one intersection. So the sign is minus 1 to the 1. So the sign of this permutation is minus 1. It's an odd permutation. It's actually called a transposition when it flips two elements. And actually, all transpositions are odd, which you could try to count by drawing the diagrams and convincing yourself that this is true. In general, the sign is minus 1 to the n, where n is the number of intersection between pairs of line segments. And in this case, n is 1. And see if you can prove the theorem that says the sign of a composition is a product of signs using these intersections. And these are really important. So you could use them to prove certain positions on a Rubik's Cube are impossible because it has to do with parity, or positions on a slide puzzle, like it's a square with one hole left for you to move the slides, and other orderings of many other things. So here is an alternative definition, which is very abstract. Uh, if A has entries Aij, then the determinant is the sum over all permutations. So this sum has n factorial many things. The sine of sigma times A1 sigma 1, A2 sigma 2, and so on. So we're going to describe and do examples of this. And let's talk about why the rule of Saris doesn't work for 4x4 and higher dimensional matrices. Basically, it has to do with the fact that if I try to permute 1, 2, 3 with each other, and 1 goes to 2, 2 goes to 3, and 3 goes to 1, then there's only two ways to permute these three objects without fixing one of them. So in this case, 1 to 2, 2 to 3, 3 to 1 has no real starting point. We just 1 is an arbitrary starting point, but 3 goes to 1, 1 goes to 2, it kind of goes in a circle. And so it's the same as any of these other three. 1 goes to 2, 2 goes to 3, 1 goes to 2, 2 goes to 3. So these are all the same. These are all labeled by 1, 2, 3. 1 goes to 2, 2 goes to 3, and then we loop back around to 1. So there's one that is not equivalent. There's one 3 cycle that's not equivalent, which is this one. So instead of 1 going to 2, 1 goes to 3. And in this case, like 1, 2, 3 is 2, 3, 1 is 3, 1, 2. Usually we write it by writing 1 first. Then that kind of fixes what the rest should be. And these 2, 3 cycles represent sum of the left to right diagonals of a 3x3 and subtracting right to left diagonals in a 3x3 in some way. but this doesn't hold for 4 by 4s. So a determinant of a 2 by 2, now let's do this with permutations. So let's use the formula. There are 2 factorial, which is 2 permutations. The identity, which is usually called 1, 1 goes to itself, and we leave out all the other information. So 1 goes to 1, 2 goes to 2, and the transposition swapping 1 and 2, usually labeled 1, 2. So the determinant of A is equal to the sum over everything in S2, which is just those 2 permutations. There's identity, 1 goes to 1, 2 goes to 2. And then there's the transposition, 1 goes to 2, 2 goes to 1. So the sign of the first one is even, the sign of the second one is odd, and this is what we get for the determinant. But that's exactly AD minus BC if we replace it with A, B, C, D letters. What about a 3 by 3? So for a 3 by 3, there's 3 factorial, which is 6 permutations. There's the identity that keeps 1, 2, 3 fixed. That corresponds to the diagonal. There's 3 transpositions that swap I and J. So it swaps 1 and 2. It swaps 1 and 3 and leaves 2 fixed. And it swaps 2 and 3, leaving 1 fixed. Those are odd. All transpositions are odd. And then there's 2 3 cycles, 1 2 3, and 1 3 2. And that's how we sum over all of these possible permutations. So all transpositions are odd by considering the diagram in figure 2. Which one is figure 2? This one. So all transpositions look more or less like this. If you swapped 1 and 3, you have to be careful so that they don't intersect at 2 at a single point. In that case, you will get 3 intersections instead of 1 intersection. Either way, it's odd. So the permutations 1, 1, 2, 3, and 1, 3, 2 are even because there's 2 intersections. So here's 1, 2, 3. 1, 2, 3 is even. There's 2 intersections. It's minus 1 squared. Here's 1, 3, 2. 1 goes to 3, 3 goes to 2, 2 goes to 1. And then we make these lines. There's 2 intersections, so it's also even. In fact, all 3 cycles are even because they can be written of a product as a product of 2 transpositions. So another way to prove 1, 3, 2 is even is more algebraic. We checked 1, 2, 3 is even, and now the product 1, 2, 3 composed 1, 3, 2 is actually identity, which is also even. Therefore, 1, which is the sign of this permutation 1, is sine of 1, 2, 3 sine 1, 3, 2 by the theorem. And sine of 1, 2, 3 is 1. So we could plug that in, and we conclude that sine of 1, 3, 2 is 1. And this leads to the following computation for B, which is our 3 by 3 matrix. So here, except A should be replaced by B. The determinant is we have the permutation 1, which is A11, A22, A33. We have the permutation 1, 2, 3, and we have the permutation 1, 3, 2. And you should compare this with figure 1, which was this Saris rule up here. So we have identity. We had this starting at B going left to right was corresponding to 1, 2, 3, and starting at C going left to right corresponding to 1, 3, 2. And then you could subtract all the transpositions. The one swapping 2, 3, the one swapping 1, 2, and the one swapping 1, 3. And here's a pattern. A permutation can be thought of as a path from an entry in the top row to an entry in the bottom row, passing through exactly one entry in a column each time. So only one entry per column is passed through, and all columns are passed through because of that. And the sign represents the various ways we can order n integers. So the various ways we could pass through. So for example, here's a path from A13. So we go from A13. Now we can't use this column anymore. Go to a different column, A21. We can't use this column anymore. And now only A32 is left. For the red path, start at A13. Okay, and then go to A22. Now we use this column. Now there's a unique entry left. So here, there were a few entries at this point. We could have gone to A21 or A22. And the green one goes to A21, the red one goes to A22. And these last two are uniquely determined for both of them. And what we're summing over in this new definition of determinant is all the possible paths with the sign of the corresponding permutation included. And uh, the rule of Saris doesn't work anymore for 4x4 matrices because of a few reasons. So there's only 4 right to left and 4 left to right diagonals in a 4x4. In a 3x3, there were 3 left and 3 right diagonals, but 3 plus 3 is actually 3 factorial. But 4 plus 4 is 8, which is way less than 4 factorial. So there are many more permutations to consider in a 4x4. So that's one problem. Let's consider the following. There's permutations 1, 2, 3, 4. So it swaps 1, 2 with each other, swaps 3, 4 with each other. And this one takes 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So here, the green arrow, wait, figure 9. Oh, that's not the one that I wanted to do, actually. So the green arrow represents the even permutation 1, 3, 2. So 1 goes to 3, 2 goes to 1, 3 goes to 2, and 4 goes to 4. So the green one is 1, 3, 2. This is a typo. This should be 3, 2. And the red arrows represent 1, 4, 2, 3, because 1 goes to 4, 4 goes to 2, 2 goes to 3, and 3 goes to 1. And that represents this path along the matrix. And it's an odd permutation because it's a product of odd number of transpositions. So each of those are odd, and there's an odd number of them. So it's an odd permutation. And this shows just 2 of the 16 permutations that are not produced by diagonals. You see, these are not from diagonals. The unique diagonal containing this has to be this. And the unique diagonal containing, well, A13, A21, that's not a diagonal for sure. If it's a diagonal, it would have to contain these, but then that would be just this one. Diagonals. Another problem is that now the right to left diagonals aren't always positive, and the left to right diagonals aren't always negative. So this left to right diagonal is actually positive, and this right to left diagonal is positive, and this left to right diagonal is negative. So the green arrows represent the permutation 1, 2, 3, 4. 1 and 2 were swapped, and 3 and 4 were swapped. And the red arrows represent the odd permutation 1, 2, 3, 4. 1, 2, 2, 3, 3, 4, 4, 1. So that's negative despite being left to right. And 1, 2, 3, 4, 1, 2 separated 3, 4 like this was right to left, but it was positive. So here's all 8 of the diagonals. So you have the left to right diagonal corresponding to 1. That's this diagonal. You have 1, 3, 2, 4, which is this other diagonal. So now every other diagonal is positive. This one was positive, and this one is positive. Oh, this one. Those two are positive, and these two are negative. So some diagonals are now positive. It's a lot harder to visualize to use the rule of Saris. And Yeah, so here's all 8 of the diagonals, and there's 24 different permutations. So there's 6 4 cycles, 3 factorial 4 cycles. There's 3 products of disjoint transpositions, like 1, 2, 3, 4. There's 8 3 cycles and 6 transpositions and the identity. So that's 24 permutations total. And you could try to play around with this and show that actually half of these are odd and half are even.